Witam ponownie wszystkich przed ekranami. Cieszę się, że wciąż śledzicie to, co dzieje się od samego rana podczas pierwszej w historii Studenckiej Konferencji Kosmicznej. To dopiero, jak wspomniałem, pierwsza konferencja, ale co mówiłem też na początku tego dnia, jest to ta konferencja, która otwiera cały cykl i mamy nadzieję, że co 2 lata takie konferencje będą organizowane przez Polską Agencję Kosmiczną, najpewniej we współpracy z uczelniami, tak jak to ma miejsce teraz. Przypomnę, jesteśmy na Politechnice Gdańskiej. To tu właśnie dziś rozmawiamy między innymi o otwarciu pierwszego w Polsce i 14 w Europie ESA Labu. Zakończyliśmy sesję panelową. Mam nadzieję, że te dyskusje panelowe, prezentacje, które tam były przedstawiane, bardzo Wam się podobały, a jeżeli z jakichś przyczyn nie widzieliście wszystkiego albo przegapiliście transmisję, zawsze można je będzie znaleźć na naszym kanale na YouTubie. Tam pojawią się po zakończeniu i nie wiem, czy będzie to dziś, czy jutro. W każdym razie w niedalekim czasie będzie można te zapisane wideostreamy sobie obejrzeć. Cały czas próbujemy pokazywać, że przemysł kosmiczny to jest ta gałąź gospodarki, która nie tylko rozwija się bardzo dynamicznie, ale w niedalekiej przyszłości będzie dotykała bardzo wielu dziedzin naszego absolutnie codziennego i ziemskiego życia. Już dziś korzystamy z nawigacji satelitarnej, korzystamy z prognoz pogody, korzystamy z telekomunikacji, która właśnie wykorzystuje łącza satelitarne, a tych usług, które świadczyć będą firmy kosmiczne, a z których korzystać będziemy my, będzie więcej i więcej każdego roku. Jeżeli szukacie jeszcze takich abstrakcyjnych przykładów na to, jak mogą wyglądać badania kosmiczne, to chcielibyśmy Wam zaprezentować właśnie taki przykład. I pozwolą Państwo, że przejdę teraz na język angielski, bo ponownie dołącza do nas gość z Europejskiej Agencji Kosmicznej. So I'm switching to English right now as we are joined by our next guest. This is Christophe Lasseur from European Space Agency. Christophe is going to talk about his research on plants in space. Yes, this is actually happening. So, Christophe, I'm really eager to hear about how you and other scientists are investigating how plants behave in space. The floor is yours.
Thank you very much. Thank you very much for this invitation and this opportunity to present our work. I will try to share my screen. I hope it works.
We're waiting for the screen to appear. It seems like oh, here it is.
May I start?
Yes, yes, you can. We can see your screen. We can hear you not very well, so if you could speak a bit louder, it would be great. But other than that, it's fine.
Okay, very good. So thanks very much for this invitation. It's a pleasure to speak about human on Mars and human on Earth. This little provocation in the title, I will explain you why. So, within the European Space Agency, I am in charge of the life support domain. And the life support domain is to simplify all the technology we place around the astronaut to keep them alive. So on this picture, you can see the pool of the 6 European astronauts. And the one with glasses is me, because I have as well the chance to be an instructor of the astronaut. Yeah? So, astronauts, as human, to survive, need oxygen, water, and food. On Earth, we do not realize the pleasure we have to have this capacity, but in space, of course, we have to organize everything. And of course, the astronauts produce waste, urine, fecal matter, CO2, but as well some traces elements, which are not so well known because they are almost invisible, which are perspiration, chemical contaminants, and these days everybody is very sensitive to microbial contaminants. So a need to rebuild this environment in space. But let's do first basic calculation. Maybe you don't realize, but just to stay alive, so I'm speaking about the minimum, you need 5 kilos per person per day. Yeah? So if you consider a crew of 6 and a mission of Mars will be somewhere around 1,000 days, then you reach somewhere around 30 tons. Yeah? And this, if you put now a bit of hygiene, such as shower, changing clothes and everything, it will be somewhere around 100 tons, which is far, far above the capacity of the current launcher. So here we already have a problem before we start. Something that which is not always well known is, of course, the space vehicles are limited in mass, are limited in volume, so they are quite airtight. And this means that the human density, the surface density on board the space vehicle is very high. If you compare to Singapore, for example, you see that already in surface is very high. But if you compare in density, on Earth, we more or less have 3 kilometers of air above us. On board the space vehicle, they will have somewhere around 80 centimeters to 1 meter. So you see, any concentration of contaminants will accumulate very fast. So the risk is even enhanced. Today, how it works? So today, on board the International Space Station, we have a very basic and very simple strategy, if I may say. We have the chance that the International Space Station is orbiting around the Earth, more or less at 400, 500 kilometers. And this gives us a chance to regularly send some cargo. Yeah? And within this cargo, we place water, oxygen, and food. Yeah? You may have seen pictures of the astronauts eating fresh food when it arrives. And all the waste are placed in the vehicle, and this vehicle is burned in rear food. That's a very basic approach, but it's quite robust because it has been working like that for the last 20 years and even before with the Mir station. The problem is tomorrow, because tomorrow we will quit the Earth orbit. We will go to the moon, we will go to Mars, and at that time, this strategy of transportation, of regular transportation, doesn't work. So this means we have to recycle absolutely everything on board the space. And this is why people are often speaking about circular economy or circular system. So, of course, there is not one technology who take all your waste, transform them, and give you oxygen, water, and food. So this means you will have to assemble processes, technologies, such as filtration, catalyzer, microbial degradation, and so on, to have the highest level of closure. What does it mean? In fact, the lowest amount of mass to transport. And of course, this has to be very safe because this is the survival of our crew members. So how do we do this? We have what we call a criteria, a metric, which is called ALICE, which stands for Advanced Life Support System Evaluator. Yeah? And we compare all the systems with their mass, the efficiency of transformation, the energy, of course, there is no energy, the safety, it has to be very safe, so sometimes it has to be duplicated, which is more mass and so on. And of course, the crew time, because the astronaut is not in space to manage the maintenance, he is in space to do research. So that's very important as well, that we take into account this parameter. And with this kind of spider, we are able to elaborate or to select the one which is the best for a mission. But what does it mean? This means at the beginning, we will define what we call the requirement of the mission. Where do we go? How many people? Which launcher? Which energy? How long time? And all this will be, let's say, the basic of the definition. And then we will study different possibilities, different systems, and we will have to compare them in their dynamic behavior, in their mass, in their structure, in their reliability, robustness, safety, and so on, and of course, in the astronaut activity. So all the engineers will be able to play with their own, let's say, their own generic tool that they know quite well, this is their business, and they will work together in order to be able to extract this parameter. And every time we will add a modification or we will reconsider a new technology, then we will recompare this new metric. So the MELISA project, which is the European project in this domain, which stands for Microecological Life Support Alternative, has been started to simplify 30 years ago. Today, it represents in the order of 45 organizations. What does it mean? It means university, private company, space company, and it's spread over 12 European countries, including Canada. So it's a teamwork. As you can see, this is the Melissa team. It's a teamwork extremely multidisciplinary. You will have engineer, you will have medical doctor, you will have nutritionist, you will have microbiologist, you will have plant physiologist, you will have a mathematician, you have genetician, and all these people are working together. And this is as well one of the challenges of the project. But it is as well from time to time, and let's say, a research project. We have activities which are low TRL, or maybe it's more, let's say, at the feasibility study. This is why we welcome as well quite a good number of PhD. And for those who have, let's say, good eyes, the two charming ladies in the middle are coming from Poland. Okay. So the Melissa project, in fact, start Melissa. You have to know that it starts from Airbus. It doesn't come from the air. It really starts from Airbus. At that time, it was called Matra Espace. And they got inspired by a terrestrial ecosystem. They thought, okay, this, if we could duplicate the Earth ecosystem, we have the solution. But of course, we cannot duplicate the Earth ecosystem because it's too big, it's too, let's say, complex. We don't understand it too much, as we can see these days. So it wasn't necessary to simplify it in order to be able to apply engineering control. Because today, if we would, let's say, place all these organisms in a big box, then of course we have to dream that it will work. And others have tried this, and as you probably know, it doesn't work. So we have to be a bit more deterministic. This being said, if you consider the function of this leg, starting from the bottom going up, you will realize that if you place each layer in a tank, in a compartment, then you will have this perfect cycle, starting with compartment 1, which is the bottom part of the leg, no light, Going a little bit higher, compartment 2, you will have already a bit of light as a source of energy. A bit higher again, you will have oxygen, so you will be able to oxidize mainly urine, which is the preferred nitrogen source. And then you arrive at what we call the producer, and the producer is split in two parts, the plant part and the algae part. And this plant and the algae part will do the job to produce oxygen, water, and food. Why do we put biology? Probably you never realized, but today we are not able to synthesize all the molecules of a perfect diet. So this means we have to go biology. We have to go tomato, we have to go lettuce, we have to go cows, we have to go veal, we have to go rabbit if you want, or fish, but we have to go biological. This is the only way. And this is one of the complexity of such a project, is to bring biology as a technology to solve an issue. And this is new in the space world, to consider that we could use biology as a technology. So of course, this means that we will apply all the basic of engineering in order to understand the process continuously and be able to drive it, because naturally the system is not stable. You really need a lot of engineering tools. So what are the challenges? You have seen it's several processes together. This means every process has to be efficient, otherwise the loop is not efficient. The processes has to be compatible. If the first process produces 1 ton per minute and the second one only swallow 100 kilos, then you have a big accumulation. Its mass, its buffer, its pumps, so big issue again. You will have to be able to understand, model, mathematically model, and control biological processes. Of course, today it looks obvious, but 30 years ago when we started the project, was not that obvious. You cannot limit your thinking to carbon and nitrogen. If you open newspapers these days, you speak about the difficulty of the quality of the environment and so on in terms of carbon, in terms of nitrogen. But you cannot limit your thinking to these two elements. To simplify, you should almost treat the complete Mendeleev table. It is cycles, but it is cycle in terms of solid, in terms of gas, in terms of liquid. They have different kinetic, different speed, and of course you cannot allow drift, so this has to be controlled. What you will produce has to be accepted by the crew and has to be safe. So that's to simplify the key challenges of the project. How do we do this? We start normally very often at the university level, and this is an example. Yeah? So let's say we work with PhD for a few months, and we start to look at the feasibility, the characterization, preliminary models that we call stoichiometry, which are more or less, to simplify, chemical formula. We apply the first Lavoisier principle, what goes in, what goes out, and all this kind of things. And when this is done, then we go at pilot scale. So really, let's say, much more robust and serious engineering. Yep. This is the same bioreactor than the one you see before, but also completely full of analyzer, sensor, and so on, in order to be able to drive the process. It is a closed cycle, so every process has to be driven by the computer, by the mathematical model. So it has to be very robust. And once this is validated, and we know it works very well, then we will put it in space, and this sugar box that you have on the table is the same. It's still performing the same function, of course not at the same amplitude, but the same function. We put it in space and we validate if it works. If this three steps has been done properly, we can already size the life support system for a moon mission, a Mars mission, such as the hardware you have here, which is, I would say, almost in the capacity to be already developed or manufactured. Yeah? So just a few words about what we have already done in space. You don't access space when you want. It is an international competition between NASA, Russia, Japan, Europe, and Canada. And if you are selected, if your proposal is of good scientific value, then you will have the opportunity to fly. So all the black ones have already flown, either on board space station or Photon with the Russian collaboration, for example. And the green ones are the ones which are approved, but which are in development. And for you to know, the WAPS one is the one with plan. So the last one who flew on board the International Space Station was called Artemis, and this one has double S, so do not confuse it with the NASA program. And this one has demonstrated that we can grow algae in microgravity. We have 4 culture of microalgae, and we demonstrate then we can produce oxygen and we can produce biomass which is edible. So that was over a few weeks. And of course, we are doing a scaling up in order to do it for a much longer duration. So you will never fly a Melissa loop, or let's say a life support system, if you want to be more generic, without a very robust ground demonstration. And you cannot demonstrate recycle if you don't have waste. Yeah? So first, on ground, we are comparing our technology, operating our technology for quite a long duration in order to be sure that the diversity of waste is not a problem. And this is what we do in a specific facility, which is in Barcelona, in the campus of University Autónoma de Barcelona, where we are able to progressively integrate our technology. We use human waste, but for cost and safety reasons, we do the demonstration of oxygen CO2 with a rat compartment. So we don't do animal research, and the animals are there just to consume the oxygen and produce CO2. They are completely connected on the gas phase to the microalgae compartment. I mean, the habitat of the rat is extremely airtight, at the same level of airtightness as the space station. Yeah? And it's connected to the algae, and the computer will drive the algae efficiency, the algae performance to follow the activity of the rat. And now, up front of the algae, we have what we call nitrification. So to simplify, we transform urine in the proper substrate to be able to grow the algae. So two ways, urine and CO2, give us oxygen and protein, which is edible. So you can see on this table, then the operation, this is a blue line, is very stable, is defined by the operator, and is very stable by step, and we can really control fully automatically the performance of this hardware. So all this is very nice, but you may wonder why we spend so much time, 30 years of research, for only 6 astronauts. In fact, you will very rapidly realize that the challenge of a system such as MELISA has a lot of interest for terrestrial application as well. The first one that you may have heard, and I think it's quite popular in Poland these days, is Roland Garros tournament, where we recycle all the grey water of the tournament 2020, 2021, 2022. So the grey water consumed by the tennis woman and the tennisman is fully recycled by MELISA technology. We have as well very popular generally in the student community beer. So as you may know, to produce beer, you need to consume a lot of water. You produce as well a lot of biomass. It's a fermentation process. And there is a brewery, quite a well-known brewery, which is called La Trappe, where we have implemented our MELISA technology to reduce the environmental impact factor. A building which is currently in construction in Paris, totally colonized by microalgae on the side. And this will give us the opportunity to produce biomass of high value, as well as to fix CO2. And I have to express that this building will be not duplicated, but the same function will be more or less implemented in Amsterdam, but including plants as well. Another one which is called EasyCol, it's a MELISA spin-off company, and it has the, we discover, it's called serendipity, if you want to use the proper word. We discover a bit by coincidence that one microorganism of MELISA has a very strong effect on bad cholesterol. So we took 15 patents, we demonstrated on humans twice, I mean, 2 campaigns, and now we are talking, of course, with the big pharmaceutical group. Now I want to be back a bit to the students, just to give you 2 examples. Speaking a bit on the left side of the Yolin Depa, on the right side of Lucie Poulet. Yeah, they both joined ESA as master students. They both have a MELISA PhD. Yeah, they were able to stay with us. We like them very much, so they were able to stay with us for a PhD. And at the end of the PhD, Yolin started a spin-off company, and Lucie has joined NASA in Florida. So on one side as well, you could see that Yolin got a prize of the very big company, industrial company ArcelorMittal for our work, and Lucie already participated to a test campaign. So thank you for your attention, and I invite you to follow MELISA activity on the social network by following some of this, and of course, if you are interested, to consider when there is call for PhD. Thank you for your attention.
Thank you, Christophe. To był Christophe Lasseur z Europejskiej Agencji Kosmicznej. Dziękujemy bardzo raz jeszcze. Thank you once again. Merci beaucoup.